Alright, so let's go over a related rate example. I apologize for the small type here, but here it is. It says, suppose a bird is flying horizontally 40 feet above your head at 20 feet per second. How fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? So whenever you're dealing with a related rate problem, if it lends itself to a picture, you should really work to draw a good pictorial representation of what's happening in the problem, and that way you can start seeing the math that's involved in making connections. So there you are, there's the bird, and so let's start adding some things to the picture here. And so I'm going to start the angle of elevation right there. Well, that's not the angle, but that's the line of sight. And then we got our vertical sight over here, and then we got the horizontal leg. So we got a nice right triangle picture here. We're told that the bird is 40 feet overhead. So whenever you're labeling these pictures, you want to label things that are not changing with their values. And so the 40 feet is not changing. So we'll label that here 40 feet. But we know some other things are changing, and so we want to label those with variables, with letters, because they're not constant. This length here is not always going to be 30 feet, as the problem says. It says when the horizontal distance is 30 feet. That distance is changing, and so we don't want to put 30 there because that gives us a misunderstanding of the fact that this is a dynamic situation. Things are changing. Whereas our picture is static, so we have to represent as best we can a dynamic situation in a static picture. Other things are changing too. The hypotenuse is going to change if the bird is moving away from you, and we might want to label that, although we might not need it when we actually go through solving the problem. The angle here is going to be changing, and so we're going to label that theta. The other angle up here is going to be changing as well. I don't think we're going to need it, so I'm not going to label it, but you can. It doesn't hurt. So going back to check the problem a little bit. So they tell us that the bird is flying horizontally at 20 feet per second. Okay, so the next thing we want to do once we have a good picture is we want to start interpreting other quantities that we have in the picture in terms of other quantities we have in the problem in terms of the variables that we have in the picture. Since the bird is flying horizontally and our horizontal distance is named x in our picture, we want to relate that 20 feet per second to x in the picture. Now x is the length, and the 20 feet per second is the rate of change of x. And so we want to list the 20 feet per second as the derivative of x with respect to time, dx over dt. Now we know it's dx over dt and not dx over some other letter because the units of the problem, the 20 feet per second, feet on top means that, dx, it's a length, so it should be in feet according to this problem. And then time in seconds on the bottom tells us that we are differentiating in this problem or measuring how things change with respect to time. And so dx over dt is going to be 20 feet per second. Anytime you have one of these problems, you want to make sure you understand whether or not the quantity that we're measuring the rate of change of, we want to know if it's increasing or decreasing. And I'm not sure if the problem is very clear on that, so we might have to make an assumption. Let me go back for a moment. Suppose the bird is flying horizontally at 20 feet per second. So it doesn't tell you if the bird is flying towards us or away from us, and that would matter. I guess I kind of assumed in how I drew the picture the bird is kind of flying away from us. Maybe not really. But if the bird was flying away from us, then x would be getting larger, so then the derivative of x with respect to t would have to be a positive number. And if the bird was flying towards us, then dx over dt would have to be a negative number because x would be decreasing. And that's something that you should remember from when dealing with when a function is increasing, its derivative is positive. When a function is decreasing, its derivative is negative. Those types of relationships. Since I'm going to assume that the bird is flying away from us, then we're going to use a positive 20 feet per second. So once we have a good picture and we've labeled it and we've interpreted some of the values that we have in terms of the variable quantities in our picture, we also want to interpret the question that's being asked in terms of the variable quantities in the picture. So it says, how fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? So we want to know how fast the angle of elevation is changing. So in our picture here, theta is the angle of elevation. So we want to measure how fast that's changing. So I like to say that we need to write, a sentence. Excuse me. We got to translate this sentence into some math symbols. So we want to find d theta over dt when the horizontal distance, which is x, is 30 feet. So when we've been able to define, when we're able to define the question in terms of the variables that we have, then we're on our way to solving the problem. The next thing we need to do is we need to put some math to the problem. So we need to, since we're trying to find d theta over dt, we need to find a relationship, an equation that involves theta that we can then use to generate an equation involving d theta over dt. Then we can go ahead and start trying to solve it. Now there may be more than one equation that we could use. We want to, find the one that works with the data that we have. So in other words, if we have one equation, we start to work it out, we find out we don't have enough data to finish that problem, then that might not have been the best equation to start with. There's often more than one equation that's useful. And so we want to make sure that we find something that's involving the quantities that we need. They didn't tell us anything in the problem about z, and so I don't think we want to use z in our equation relating theta to the other variables in the problem, because they didn't tell us any information about z. So let's go ahead and not use z. Let's use the 40 feet, because we know that's always going to be there. We know x is going to be there, and x is changing. So the relationship between theta, the 40, and the x is our tangent ratio. So tangent of theta is going to be 40 over x. And so this gives us a relationship involving theta and another variable in the question that hopefully we could use to solve the problem. And it looks promising because we do have a relationship involving dx over dt, so when I differentiate this implicitly with respect to t, I'm going to be able to utilize dx over dt when I solve the problem. Okay, so that'll be our next step. We're going to implicitly differentiate with respect to t. So d over dt tangent theta is equal to d over dt of, it's 40 divided by x, but I would rather rewrite that as 40 times x to the negative 1 instead of having to use the quotient rule, because the power rule is easier, so I'd rather do it like this. And as a side note, this equation can be solved for theta using the inverse tangent function. So if you don't want to implicitly differentiate at this step, you can decide to say, let's rewrite this as theta is equal to the inverse tangent of 40 over x, and then take the derivative that way. At this point, you should know the derivative of it is inverse tangent. And it's perfectly a valid way of solving the problem. I'm just not choosing to do it that way. So, continuing here, taking the derivative of tangent, we should know that is secant squared theta. Now we're differentiating with respect to t, and so we have to use the chain rule here. So we have to multiply this quantity times d theta over dt, the derivative of the inner function. And then let's go ahead and take the derivative of the right-hand side. So we're going to end up with negative 40 x to the negative 2. And again, since our variable is x and we're differentiating with respect to t, which is different than x, we're going to have to multiply that times the derivative of the inner function, derivative of x with respect to t. That's the chain rule. And if you still need some support on that concept, then let me know and I can point you to a video that might better explain what's going on there. So let's kind of take stock of what we have here and see if we're going to be able to solve the problem. So I'm looking for this d theta over dt. That's what the problem was asking us to find. So we're looking for that. I know dx over dt. They told us that. Let's go back. They told us x. That's 30. Okay. So I got these two quantities. So we're good to go there. The only thing I don't know, making sure I got everything here. The only thing I don't know is theta, or even better, I don't know secant theta. I need to know this quantity here in order to solve the problem. So if I can't find secant of theta or theta, one or the other, there's a couple different ways of approaching this, then I'm going to be stuck and I'm not going to be able to solve this problem. And I might have to go look for a different equation relating theta to some other variable perhaps, that I can then use to solve the problem. So hopefully I can solve this. Let's see what we can do. So let's recreate the picture here as best we can. So we know this is theta, and let's do this picture in the moment that we're trying to solve the problem, when x is equal to 30. So when x is equal to 30, well, we have this picture here. We know by the Pythagorean theorem that we can find the hypotenuse, and hopefully you recognize this as a 3, 4, 5 right triangle times 10. So we know the hypotenuse is going to be 50. And then if we remember secant is the reciprocal of cosine, then I can figure out the cosine of theta from this picture here as, cosine is adjacent over hypotenuse, so that's going to be 30 over 50, which reduces to 3/5. Then I can tell that secant of theta is going to be 5/3. And then secant squared theta is going to be 25/9. And now I have that other quantity that I need in order to solve the problem. All right, so let's go plug all this stuff in over here and see if we can finish solving for d theta over dt. So 25/9 times d theta over dt is equal to -40. Now I'm going to move that looks horrible. I'm going to move the x squared to the bottom because it's x to the -2, and I got to remember that that is in the denominator. Some students tend to forget that, and I don't want us to have that happen. We said we're doing this when x is equal to 30. Just double checking. So this is going to be 30 squared down here, and then we were told that dx over dt is going to be 20. So now it's just a little bit of algebra to solve for, basic algebra to solve for d theta over dt, and so what do we get here? So we're going to get -800. I shouldn't be squeezing this in, at least maybe not with the same color, so it stands out. So we get -800 when I multiply the 20 and the -40. 900 on the bottom, which of course we're going to cancel zeros out there. When I multiply by the reciprocal of the 25/9 to move that over, we get 9 over 25 here. And whatever that works out to be, we can do that really quickly. I was going to leave that to you to do, but that's just me being lazy. The zeros here are going to cancel. The 9 then is going to cancel with that 9, and we're left with -8/25 as the rate of change of that angle. One last question you might want to think about, and I'll let you think about it for just a moment before I tell you the answer, is what are the units of d theta over dt? That's a common question that gets asked for these related Word 8 questions to give the correct units for the problem. So I'll pause for just a second, and ask yourself, what are the units? Well, in calculus, remember, here's the answer. So if you're still thinking about it, pause the video. In calculus, remember, we prefer radians over degrees. So if we look at our ratio that we have over here, d theta over dt, theta is in radians. Our time was given in seconds, and so this ratio, -8/25, is going to be radians per second. Whoops, that should be radians like that, per second. I guess I could just use S. Wow, I keep going backwards to worse and worse things. Let's do it like that. That looks better. All right, so hopefully that was helpful, and if you need more, let me know.